with defining various subsets within the real number system. Okay, the first subset are the natural numbers. The natural numbers are sometimes described as the numbers we use when we count. So 1, 2, 3, 4, and we don't count with negative numbers. We also don't count 0. So counting how many things you have would include positive numbers. 1, 2, 3, and on and on. So the natural numbers are those set of numbers. Now, these sets build on each other, so whole numbers include all of the natural numbers as well as 0. So the whole numbers are 0, 1, 2, 3, and on. The next set of numbers is the integers. Again, it builds on the other sets. Integers include the natural numbers, so all those positive numbers. It includes the whole numbers, so it includes 0. But integers also include negative numbers. -1, -2, -3, and on. So the negative numbers, 0, and positive numbers. Rational numbers encompasses groups, and it actually encompasses any number that is defined as such. A divided by B shows that a rational number can be expressed as a fraction. And a rational number is one where A and B are integers, and B is not 0. Remember that you can't divide by 0, so B cannot be 0, but it can be any other integer. And when a rational number is expressed as a decimal, it's either going to terminate or repeat indefinitely. For example, if I have the fraction 1/4, I can express that as a decimal 0.25, and this clearly terminates. It has an end. However, if you consider some other fractions, such as 2/3, this just goes on 0.666666, but it's repeating. It's not changing to all different numbers. It's repeating. And repeating decimal could also, it doesn't have to repeat with just one number. It could be 0.323232 and on and on. So if it's either terminating or repeating, a fraction that either terminates, when expressed as a decimal, either terminates or repeats, it's a rational number. A couple of other definitions. Square roots. We define a square root of a number A is a number B satisfying B squared equals A. So this is much easier to understand when you plug in some numbers. For example, if I let A equal 4, then B is going to equal 2, because 2 squared equals 4, or 2 times 2 equals 4. So we can say that the square root of 4 is 2. So the square root of 4 is 2 because 2 times 2 equals 4. And then we sometimes use this symbol to express that we are finding the square root of a number. Irrational numbers also belong to the real number system. So we just talked about rational numbers, and rational numbers, again, can be expressed as a decimal that either terminates or repeats. Irrational numbers cannot be expressed as fractions. In fact, when they're expressed as decimals, they're actually non-terminating and non-repeating. So if I gave you some number that just went on, and it never developed a pattern, and it went on indefinitely, that would be an irrational number. Another example is actually pi. And pi goes on when expressed as a decimal form indefinitely. A lot of times we just take it and we say it's 3.14, and we take it to the hundredths place, and that's enough for the purposes that we usually need it for, but it's actually an irrational number. In addition, the square root of any number that is not a perfect square is an irrational number. A perfect square is created when an integer is multiplied by itself. So an integer multiplied by itself creates a perfect square. So if I have 2 times 2, I get 4. That's a perfect square. Or 3 times 3 equals 9. Well, if I take the square root of 4, it's 2, and the square root of 9 is 3, those are not irrational numbers. Those are rational numbers. However, if I take the square root of 2, that's an irrational number. All of these are irrational numbers. Number system contains all rational numbers and all irrational numbers. In the beginning, I said that real numbers are those numbers that can be expressed on the number line. So if I gave you some examples, such as -5, -3.67, -1/2, 0, 1, and these are all rational numbers, but irrational numbers would be included here as well. For example, I could have pi. I could put pi on here. I could put the square root of 10 on here, or the square root of 2. So the real number system contains all the rational numbers as well as all the irrational numbers. So all the things that we talked about. Here's a decimal that terminates, a negative number that's a fraction, 0. A positive number, pi, which is an irrational number. In this example, we're going to talk about what sets of numbers various numbers belong to. So, to what sets of numbers do the following numbers belong? And they give us 3 different numbers. Looking at -7, it's a real number. It can certainly be expressed on the number line. And then I think, is it a natural number? No, because it's negative. Is it a whole number? No, because it's negative. Is it an integer? Yes, it is. And then I think, is it a rational number? Yes, it's a rational number. So this belongs to 3 sets. It belongs to the set of real numbers, integers, and rational numbers. Here I have a fraction, and it's negative 33 over 37. Is it a real number? Yes, it is a real number. Is it a rational number? Yes, I know it's a rational number because it's being expressed as a fraction. Thinking at my other groupings, is it an integer? No, it's not, because it's not like -4, -3, -2, 0, 1, 2. It's not, therefore, an integer. Nor is it a natural number or a whole number. Square root of 8. This is a real number. As I just mentioned, the square root of a number that is not a perfect square is irrational. Therefore, this is irrational. So we have 3 different situations here. The first number, -7, is a real number, it's a rational number, and it's an integer. -33 over 37 is a real number, and it's rational. The square root of 8 is also a real number, however, it is irrational. The second example is asking us to graph the following 2 situations on a number line. The first one, A, asks me to graph the numbers -3, 3/2, and the square root of 2. So -3, -2, -1, and then I have 0, 1, 2, 3. Okay. So I look at my first number, -3. And that's pretty easy to graph here on the number line, right at -3. The second number is a fraction, 3/2, and that's equal to 1.5. So it's going to be right here between 1 and 2. So 3/2, it's going to be right there. Make it bigger. And the square root of 2. Now, the square root of 2 is an irrational number, but I can put it on the number line. I'm just going to approximate it as 1.4. So the square root of 2 is approximately equal to 1.4. And I have 3/2, which is 1.5. So therefore, the square root of 2 is going to be pretty close to that. It's going to be right next to it on the number line. So I graphed these three numbers, -3, 3/2, and square root of 2 on the number line. The second one's different. It's actually an inequality. And what this is saying is that A is less than or equal to 2.4. So 2.5's there, so 2.4 would be right about there on the number line. That's 2.4. And I see that this is telling me that it's less than or equal to. Since it could be equal to 2.4, I'm actually going to represent that as a closed circle, as a solid dot. And it includes all the numbers that are less than or equal to 2.4. So it's going to go on to the left indefinitely, and there's an arrow. So graphing two things, just a discrete set of three numbers, -3, 3/2, and the square root of 2, and also graphing an inequality where A is less than or equal to 2.4. Solid dot, and then going on indefinitely to all the numbers with smaller values. Sometimes, in order to work with an irrational number, we approximate the irrational number. To do that, we use rational numbers that are almost equal to the irrational number. Last time, when I graphed square root of 2 on a number line, I actually approximated it as it's approximately equal to 1.4. For pi, we approximate it as 3.14 in order to allow us to work with it. Okay, approximate the irrational number, the square root of 3. I can approximate that. The square root of 3 is approximately equal to 1.73. So if I needed to work with that number, I could just go ahead and, in most cases, and use 1.73. There could be some cases where I need to take it out to a farther place. In our final example, we're going to order the numbers given from largest to smallest value. And when you look at these, they're in all different forms, making it very difficult to compare them. Therefore, in order to compare them, I'm going to get them all in a similar form. I'm going to get them all into a decimal form. And pi equals 3.14. Now, this second number has a bar over the 1.4. And what that indicates, if there's a bar over the number, is it indicates that the 1.4 is repeating. I could have 1.6 repeating, and then that would just be 1.66666 and on and on. Here I have the 1 and the 4 repeating. I could even have, 7.892 repeating, and then all three of those would repeat. It would be 7.892, 892, 892, and on and on. Okay, so 3.14 with a bar over it tells me that this is just going to go on indefinitely, repeating. So I'll write it out, 3.141414. That should be far enough for now. Okay, so 3.14 with the 1.4 going on and repeating, and I have the square root of 10. So I'm going to approximate that using a rational number, as 3.162. And then I have 25 over 8. And if you figure this out, it comes out to 3.125 in decimal form. So I have all of these in decimal form, and when they're all in the same form, I can compare them. So I start out, and I want to look for my largest number. Well, square root of 10 is my largest number, okay? Second largest. Well, this is 3.14, but I don't know what comes after. And since this is 3.14 up to the hundredths place, I can't really compare them unless I take pi out to a farther value. So I have pi is 3.14159. That allows me to compare them. The ones are the same, the fours are the same. Now, as I'm going past that, these ones are the same, I'm seeing that pi is actually slightly larger than 3.14 repeating. So that is my second largest value. And right after that is going to be 3.14 repeating. Finally, the smallest one is 25 over 8. Now, I go back to what they asked me. They asked me to order the numbers from largest to smallest. Therefore, from largest to smallest is going to be, my largest number is going to be the square root of 10. Then I'm going to go to pi. After that, it's 3.14 repeating. And then finally, 25 over 8. So for this example, I had to first convert all of these into decimals so that I could compare them. And I had to take them out far enough that I was actually able to differentiate between pi and 3.14 with the repeating. And then I was able to look at them and order them as I was asked.